You know, we are literally swimming in an invisible world of signals right now. Wi-Fi, GPS, all our phone calls, it feels impossibly complex. But what if I told you that the key to understanding it all, to making it work without total chaos, is actually rooted in simple high school geometry? It all kicks off with what sounds like a pretty weird question.
It sounds a little strange, right? I mean, a wave has a wavelength, of course, but a physical length? Well, the surprising answer is, yeah, kinda. And just shifting our perspective to think that way is the secret key to basically all of modern communication.
So here's the big analogy that's going to guide us through this whole thing. We all remember vectors from physics, right? Little arrows with a certain length and a direction. Well, communication theory does the exact same thing with complex signals. A signal's length turns out to be related to its energy, and its direction is all about its unique shape or form. Now, they don't exist in our 3D physical space, but in this abstract and incredibly useful idea called signal space.
So, get this. Here's the big idea. We can take any signal, it doesn't matter how complicated and squiggly its waveform is, and we can represent it as a single point, a single vector in a special high-dimensional space.
And this transformation is where the magic really happens. It is so powerful because it lets us swap out messy, complicated calculus problems for much more intuitive geometry. We can take what looks like a chaotic jumble of signals and organize them into these clear, distinct points. It lets us literally see the relationships between them.
Okay, so if we're going to treat signals like vectors, well then they have to have vector properties, right? Things like length and the angle between them. And it turns out these geometric ideas have direct, physical meanings that are absolutely crucial for engineers. First up, let's talk about length. In signal space, we call it the norm. And here's the crucial link. The square of this vector's length is exactly equal to the total energy contained in the physical signal. Now, why should you care? Well, signal energy determines pretty much everything, from how far your Wi-Fi signal reaches to how long your phone's battery is going to last. More length, quite literally, means more power.
And just to be super clear, this isn't some convenient, made-up analogy. As experts like Simon Haken point out in communication theory textbooks, it's a direct mathematical fact. The geometry is the physics.
All right, what about the angle between two of these signal vectors? Well, we measure that with something called the inner product. The easiest way to think about it is this. If two arrows are pointing in almost the exact same direction, the angle between them is tiny, and you'd say they're very similar. It's the exact same for signals. The inner product tells us just how aligned or similar two different signals are.
Okay, so signals are vectors with length and angle. Got it. But how do we actually describe them? Well, think back to 3D space. Any point can be described by its x, y, and z coordinates, right? We can do the exact same thing with signals by breaking them down into a set of simpler, fundamental building blocks. These fundamental building blocks are called a basis, and they act just like the coordinate axes, the x, y, and z axes, but for our signal space. By just taking the right amounts of each of these basis signals and adding them together, we can perfectly construct any other signal that lives in that space. Now, for these axes to actually work properly, they need one absolutely critical property. They have to be orthogonal. In geometry, that just means they're all at perfect 90-degree right angles to each other. In signal space, it means they are perfectly independent. They have zero similarity, they don't overlap, and they don't interfere with each other at all.
And this idea, orthogonality, it is not just some neat mathematical curiosity. I mean, this is the absolute cornerstone of modern digital communications. It's the secret sauce that makes the whole thing work.
So why is this idea of signals being perpendicular to each other so incredibly important? I mean, what does that actually let us do in the real world?
The answer is so simple, but it is profound. Orthogonality means zero interference. It's that simple. If two signals are orthogonal, they can be transmitted over the same channel at the exact same time, and a receiver can still perfectly tell one from the other. It's like they're invisible to each other.
Just look at this example right here. We've got two different signal pulses happening in the same slice of time. To our eyes, they just look like a jumble of waves. But mathematically, they are orthogonal. And what that means is a receiver can tune into one of them and completely ignore the other one, even though they're all mixed together. It's like being able to listen to just one person's voice perfectly in a loud, crowded room.
And believe me, this isn't just theory. This is the engine that's running the tech you use every single day. The old 3G cell networks that use CDMA, they packed multiple calls into the same frequency using orthogonal codes. The Wi-Fi router in your house sending multiple streams of data to your laptop and your TV at the same time? Yep, it's using this exact principle. It is everywhere.
So, these perfect, non-interfering basis signals are amazing. But where do they come from? Do engineers just have to get lucky and stumble upon them? No, not at all. There is a systematic, almost beautiful, procedure for creating them from scratch.
It's called the Gram-Schmidt orthogonalization procedure. You can really just think of it as a recipe. You can feed it any collection of messy, overlapping signals you want, and it will spit out a brand new set that can represent all the same information, but is now perfectly orthogonal.
The process is actually pretty intuitive when you think about it. First, you just grab any signal and say, okay, this is my new x-axis. Then you take the second signal, and you find any part of it that overlaps with that first axis, kind of like finding its shadow. Then you just subtract that shadow away, and what's left over is guaranteed to be perfectly perpendicular to the first one. That's your new y-axis. You just keep repeating that process, removing the shadows from each new signal, until you have a complete, perfectly orthogonal set. What this procedure does is it takes a chaotic, messy jumble of signals and forges it into a perfect, beautifully ordered, interference-free coordinate system. It literally creates order out of chaos.
And that brings us right back to where we started. By taking something as complex and abstract as a radio wave and just deciding to treat it like a simple arrow, a vector, we unlock this entire powerful world of signal space. We get to trade in messy calculus for clean geometry, and by doing that, we build the very foundation of our entire digital world. It really makes you wonder, doesn't it? If simple geometry held the key to unlocking our entire wireless world, what other hidden powers are just sitting there, waiting in the abstract world of mathematics, ready to build the technology of tomorrow?